Welcome to a new edition of the History Podcast. I'm your host, Carlos Torres. Uh, our mission here is to deliver news and information regarding the heater industry by experts on the subject. And today, who is better to talk about castings and alloy than Chad Wright? How's it going, Chad?
It's going great. How are you doing, Carlos? Nice to see you.
Doing fantastic. So tell us, how's it going over there? I hear you got some snow there.
Oh yeah, we've got about 2 feet of snow here in the Midwest, and it's been it feels like a real winter again, which I'm kind of enjoying it, but I'm ready for spring, I think.
Well, everywhere is right now with a little cold weather. I don't know if you heard, but Texas is it's all stopped. So all the heat treaters there, are facing on what you face every year with tons of snow and stuff. So that's like that bread and butter to you. But the guys in Texas and in Mexico are not having a good time.
Not quite used to that.
We're not quite used to it.
Yeah.
And with this cold, it's actually nice to work in a heat treat shop, right?
Oh, I bet it feels perfect. Yeah, our guys at the foundry are a little bit chilly yet. They actually threatened to kind of cut off of a lot of our natural gas last week, but we were thankful that they didn't have to wean us down or anything like that. So we got pretty fortunate and dodged a bullet on that one.
So let me give you an introduction about who Chad Wright is. He's one of the power players of the industry. He's been on the heat treat business all his life, right? He's a second generation. He's president of Werco, which is one of the biggest foundries in the United States. And we're going to talk about the casting process, high resistant alloys, types of castings. We're going to talk about nickel pricings, chemical compositions, and the most common mistakes on castings. So, Chad, if you could give us just an introduction of your professional career, which has been very successful. What do you like to do? What you don't like to do? I mean, just share a little about yourself with the audience.
That's great. Well, thank you. Werco was started by my grandfather back in the 60s. He was a heat treater and decided to go out on his own and start his own heat treat with a couple furnaces and a couple of other guys he met. Werco stands for Wright, Isaacson, and Rodewald Company, so it doesn't have anything to do with wire, which is a common misconception. We were a heat treat for several years and then started making our own baskets in the 70s and became primarily a basket manufacturer and fabrication manufacturer in the late 70s when my grandfather passed. I started working here. So my dad and his brothers started running the company in the 70s and 80s. And I remember in the early 80s, my dad and them selling a lot of stuff that they had and borrowing money to start this little factory and continue to grow it and build it into primarily a manufacturer for heat treating projects and processes, but not doing any heat treating. I started in the 90s, was clean the toilets when I was in high school, and then after college decided to come back and work out in the factory for a couple of years, and then moved into the office, started doing quoting and estimating and purchasing and assisting in the production management. And then in the late 90s, joined the production team full-time, and in the early 2000s became the production manager. And then in 2010, my dad decided that he was going to hang it up, and I became the president of Werco at that time.
How old were you when you became president?
I was 34.
34.
Yep,
so
34.
Relatively young for a president position. How was that? How was that stress?
The stress was I'd been in this position as far as being in Werco and looking at being a leader for my whole life. So I felt like that's definitely what I was called to do. But I think I stuck with staying humble and realizing that the people I was surrounding myself that have worked there for 26 years knew a lot more about this business than I did. And I was there to help make them the best versions of themselves. So it went well. It did. When we bought the foundry in 2005, and I was a pretty young man at that time, and going down there, and some of those guys had worked there for as long as I'd been alive. And I'm like, okay, I need to come in here with respect and humility and realize what I'm here to do. So that's it's going great. I mean, we've had a lot of growth. We've met amazing amount of people all across the United States and Mexico, and in Canada as well. We've got a couple customers overseas also. So it's an incredible ride. My grandfather would have never envisioned this company being this. So we've been very blessed.
So that was my mistake. I said you were a second generation. You are actually a third generation business.
Yep. Worco was started by my grandfather in 1966.
So it was a heat treat. Then it was like a fabrication shop for baskets, and then you purchased a foundry.
Yep, we purchased the foundry, Allen Engineering and Casting Company in 2005. And so at that time we were a 30-person company buying a company 3 times that size. So that was a big challenge, to say the least. But we had been buying castings from them for years. We were their 7th largest customer. So it made a lot of sense to vertically integrate like that, so we could kind of control the entire process, which I really I think is important in our industry to keep our lead times down. Then we partnered with Saloy down in the southeast portion of the United States in 2012, and then with Hyper Alloys in 2017. So we've been fortunate to partner with long-term companies that have incredible wealth of knowledge. So it's been a great ride so far.
And I believe I have asked you this story, but maybe if you're okay, you can share it. How did the opportunity to buy the foundry came across your father and yourself? You used to
Sure.
buy. You used to buy the castings from this foundry. I believe you did a lot of business and transactions with it. But how a fabrication shop ended up buying a big foundry like Alloy Engineering?
Yeah, so we were, like I said, we were their 7th largest customer, and in 2005, I got a call from Rich Grimm, who was their technical director and my contact, and he said, "Hey, we are going to be being sold off because General Motors moved their contract that they had to sell them. They were selling them exhaust manifolds, so they were going to take that business overseas." And then essentially what happened was the company was going to go under because their assets were the collateral for the loan to GM. And so he called me and talked to my dad, talked to Chris Dankert, and we said, we need to take a look at this. So we started doing due diligence. And then in August of 2005, through a lot of hard work and efforts from people both internal at Worco and internal at Allen Engineering, we made an arrangement and took a huge leap of faith. And I've spent a lot of time down there, and so has my team. But it's been it was unique to have a fabricator buying a foundry. You've seen growth in some large foundries, but doing it that way has been great because we're, as fabricators, natural fixers of things and builders of things. So I had a lot to learn when I came in there, but I had some excellent teachers.
And actually, this is the time and the opportunity for you to share what you actually learned, if you're okay with it. So.
Absolutely.
So let's imagine this young Chad Wright steps in that foundry for the first time, and he wants to know what a high heat resistant alloy is, the casting process, and there are different types of castings. I mean, please enlighten us with what you learned the last 25 years?
So I was in 2005. So yeah, 16 years this August. Yeah. So I knew quite a bit about what I had seen coming into Worco, which was primarily tubes and return bends. But stepping back just a little bit, you're looking at different materials that you can't really identify which one is a higher nickel or chrome and which one is lower. So the first thing I had to realize was that there was a difference between your stainless steel sink in your kitchen versus these high nickel castings that I was looking at. So the first thing I looked at was, well, what is the difference and what are the different variants? So in the casting process, as most of your viewers know, you have low grade castings and high grade castings, depending on what it is that you're doing. So some of these castings that we primarily use out of HT will be 35% nickel and 15% chromium. So the variations in nickel and the variations in chrome go up and down depending on the characteristics that you're trying to exhibit in whatever kind of fixture, radiant tube, a furnace roll, a fan, a basket, a tray, a fixture. So there's the internal alloys, the things that are at more of a constant operating temperature. And then there's the items that are quenched which are carrying parts through the furnace. So I noticed the difference between those, because a lot of times the alloy selection is huge when it comes to depending, what type of a product it is.
That or product or process, right? Because we can also have retorts that are going to go to a higher temperature than regular radiant tubes for heating, right?
Mm-hmm.
There's a conception that HT is equivalent to stainless steel 330. Would that be accurate?
That is accurate, yeah. So HT is the equivalent of 330. We're able to have a little more carbon in the casting process than they can in the wrought process. So the wrought product typically has a very, very low carbon content. They can't make wrought material with a higher carbon content. So HT is pretty much the same, the 3515. Then you can get to an HU that has a little more nickel, a little higher temperature range. Then you get down into the HK versions with the lower nickel. So you really need to be paying attention to exactly what you're trying to do inside your furnace and what your operating temperatures are, whether or not that's being quenched or not, as to when you're selecting your alloy grade. And that's something I'd highly recommend that all of your viewers lean on their supplier to say, hey, this is what I'm doing. What do you think is the most ideal alloy for this condition? Because it makes an enormous difference both in price and longevity.
I believe that's a great observation, Chad, because there are different types of applications of alloy on a heat treat furnace. You can have a radiant tube, you can have a rail supporting a load, right? You can have a fan. Those are items that will be inside of a furnace, right? They can be exposed to high heat or they can be exposed to high carbon, right? So those things you have to keep in consideration. Now, there's some alloy parts that are going to be heat treated and then quenched, right? That's they're going to be on a very severe thermal shock, right? So the type of alloy that you're going to use from one application to another, it's a totally different one. Can you explain us what do we have to consider when we're quenching a part and where we're just leaving let's say a radiant tube on a pusher furnace at the same temperature for one whole year?
Mm-hmm. So certainly when you're going to be doing quenching, you've got the quench medium that you're going to be using also. So for water quenching operations, we typically recommend higher nickel elevations to make sure that it can take the extended thermal shock that you're going to have up and down into pretty cool water. If you're going to be not doing quenching, you can add things like tungsten or cobalt that'll add an enormous amount of strength and obviously money to the product that you're making. So it really depends on whether or not you're quenching, like say in a vacuum furnace also, they can use some higher temperature and higher grade materials, because in a vacuum, you're not going to have the fluid quenching. You're typically going to have the gas quenching, obviously. And so you can use some of the nickel or the higher nickel, tungsten, cobalt alloys. But if you're going to be doing the quenching, the typical batching operation, I would stick with the HT, the HU, the NC11 grades. And then depending on your operating temperatures, you might be able to get away with more of an HK variety in some of those castings as well.
And what about for baskets?
So typically the baskets have been made out of 330, RA330 in our case. We typically say it's a very good range for heat treating in the 1650 to 1850, 1900 range is perfect for the RA330 basket. We have customers that are only going up to 1400 degrees that'll use 304, and there's a significant savings. So those are the two primary grades that we typically recommend, 304 and 330.
So right here, the value I believe is that if me speaking as a heat treater, what I typically assume, which might be wrong, is all internals HT, include the tubes, tray HU, basket 330, retort HK, right? But if you share your application, your carbon percentage levels, your temperature, what you want to do with the foundry or the experts, they will give you little twinkles and tips of how you can actually improve your alloy. Would that be accurate?
Yeah. So from our standpoint, we always think it's a good idea to consider the application that you're going to put your product into, whether or not it's being quenched, what it's being quenched in, but also what your expectations are. You know, if you're expecting something to only last for a year because you're willing to take it down, then you can do a cost benefit analysis and say, listen, we can get away with a lower grade alloy in here because we're going to get rid of it every year. But if in North America, I think we see the uptime is huge. And so going with a slightly higher alloy that exhibits a different characteristic could give you a massively extended lifetime and uptime in your furnace.
So you will recommend all the users actually to contact your applications engineer and know what they want to accomplish on lifetime or in process wide before ordering just the regular alloy like they do every year, right? Because
Yep. I think that's good value that you know, your alloy supplier should be able to tell you, but they're going to ask you technical questions, right? If you're water quenching, that's a severe application, right? And an HX casting is going to do better than an HT casting in that for example.
Mm-hmm. So now let's talk, Chad, about the casting processes.
Sure.
Right. There are a bunch of casting processes. I know your foundry specializes in two, but can you share with us what are the different casting processes? You know, like
Sure.
standard one, more advanced one, what is coming? Also, and at this point, I don't really want to get into tubes right now. Just
Okay.
static castings.
Okay.
I know you could share that with us.
Absolutely. So typically whenever you're making a casting, and think about back to when they were making swords in the olden days, you would have to have something like a pattern to make an imprint into some type of medium like sand, and then you would pour liquid metal into it. So in the casting process for these high temperature alloys, they're done in typically three ways. You're going to have green sand casting, and green sand typically means a raw sand, a silica sand that's mixed with some clays and some different binders, maybe a little pixie dust. They got a little moisture to it, and then you're going to put a pattern on a molding machine and put a flask around that and compact that sand down, pull that flask off of the pattern, make the other half, and in the middle of this, these two mold halves will be the product that you're trying to make. So you'll need to have a way for the liquid metal to flow into the void that's inside that sand mold. And once you pour that metal in there, this type of metal, this HTHU, it shrinks a lot in comparison to other types of alloys like aluminum or something like that. But so it shrinks quite a bit. So the green sand is good in this case because the sand will actually move aside. So as the casting is cooling, the green sand will get out of the way and allow the metal to cool and not have any cracks as it's cooling. So, but green sand doesn't yield you typically as good of a surface finish. So if you have a casting that's touching a part, it could scratch your part. So another type of casting process is called air set. And air set, instead of compacting the sand on top of your pattern, you're actually using a two-part epoxy, if you will, that'll bind the sand particles together on your pattern. Once again, you'll pull it off the pattern and create the cavity inside there to which you'll pour your liquid metal. But that is a little harder mold, typically a much better surface finish, but the mold is harder so that as that casting cools, it can develop cracks and hot tears around certain areas that are pinched in where that rock hard sand won't get out of the way. For the best surface finish, the lost wax process is definitely what we've seen has the best surface finish. That is a process where they'll take a wax mold and picture I like the analogy of a golf head, right? So you make 6 golf heads and you make them out of wax. You glue them all together to something that looks like a shaft that they're all glued to. Then you take that and you dip it over and over again in a ceramic slurry until you have a nice outside binding on the outside of the wax. Flip that thing upside down, heat the ceramic that's now rock hard and all the wax leaks out, and then you can pour your liquid metal into that. And again, you're going to have a great surface finish with that, near net shaped products. Sometimes we do see some cracking in those castings because again, this stuff shrinks so much that you can bind in that metal so that it doesn't have anything to shrink. So if it's something that is a solid thing like a golf club, it's fine because it's not going to be bound up by any of the ceramics. But if it's something that has a lot of surface area that it could crack, like a return bend, that can be a little problematic. So those are the three types: green sand, air set, and lost wax or investment.
And which one is, because there's different final products for what you actually do at castings. But right now we're talking about trays and fixtures, return bins, internals.
Mm-hmm.
What do you think is the most optimal process, type of casting for the heat treat industry when we especially talked about trays and fixtures or
Mm-hmm.
internals?
So we see a lot of Asian castings that are made for fixturing being made out of the lost wax process because they can make them so smooth so that when your products touch them, they won't get any scratching or marring, and they're not going to pull any oil out of your furnace either because they don't have much of a surface texture. Unfortunately, some of those castings don't hold up very well. They're either made out of a lower grade alloy or they do have some cracking that you can't really see with your eye. But a lot of people are getting good life for their fixtures out of lost wax, and that's been a move to that over the last 10 years. We believe that from a tray standpoint, and any of the build-up fixtures that we've built, we've typically made those in green sand because they'll have pockets that are internal to them to keep them nice and light. And those pockets, if they have too much sand in the middle that's really hard or ceramic that's really hard, they'll get cracking in the corners. So we believe the green sand process is the best for making the trays. And there's been a lot of, and air set's kind of in the middle, right? You can take the binders in the air set and make it so that as the metal goes in there, it burns out the binders. And so the sand that's immediately contacting the metal is soft. And so if you have your binder set properly, you can actually make the air set castings be to where the sand will get out of the way and you won't have the cracks. So I realize I'm being a little bit ambiguous, but I would say the green sand for castings for trays, Pepset has moved a long way in being able to make good castings. We use Pepset to do a lot of our round products like return bends and trunnions for furnace rolls. And then in the middle of that, you put a core. So the outside is made with Pepset and it's rock hard. And the core, which is the ID of your casting, is made out of something a little softer or hollow that's collapsible.
And you, as a foreign expert, as a casting expert, what could you advise the commercial heat treaters or the heat treaters when they receive their package with a bunch of casting, let's say a bunch of trays or a bunch of tubes? If they go and do a visual inspection, what do they have to look for? Cracks, casting finishes, welding remains. What will you advise that guy which actually receive a bunch of castings before accepting it and putting in his furnace? What hint will you give them to look for just to know if it's a high quality casting? Because you just told us that the casting can look great, but it doesn't mean that it's not going to have cracks. Is there a way to help them with a visual inspection and find something?
Yeah, I think in some cases, let's take, for example, in radiant tubes, what we find is on the U-tube of a radiant tube, in the crotch of that is a very difficult place to get the metal to flow into. So if you see that there's been what looks like little pecks on there, that's been a peener that somebody's used to actually fill in little voids in the metal. So I would look for that when you're getting your radiant tubes in and say, hey, have these been peened? Can you guarantee me that they're not going to leak? When it comes to trays and fixtures, a minimal amount of repair welding and a minimal amount of grinding. And in my opinion, you would sacrifice a little bit of surface finish for less grinding, because as a casting cools, it gets a chromium oxide layer. The chromium actually comes to the surface of the casting and forms this chromium oxide layer. So if you have a ton of grinding that's going on to that casting, you've removed that layer. So look for a minimal amount of grinding, a minimal amount of welding, especially on a tray. When you have three-way intersections, in the crotch of that intersection is a common area for shrink and for porosity to form. So that's an area that I would spend a lot of time looking at if I was examining castings on the way in for trays and fixtures. And from a radiant tube standpoint, looking at the U-shaped bends. Certainly on the welding for the radiant tubes, we've seen a lot of different people have concerns about how they're welded, what they're welded with. And, you know, welds, that's going to be a natural break point of these radiant tubes and furnace rolls. So make sure that welding looks, you know, like it should.
And in other podcast, talking to another heat treat expert, we were talking about distortion on heat treat parts, right? I'm not talking about castings now. And distortion, it's a fact. You're not gonna disappear it. I mean, you can reduce it, right? But it's not gonna go away. Will that apply also to castings? Will there always be cracks, or you can have a perfect casting?
That's a great question. It's very difficult to make a casting that doesn't have any cracks or doesn't have any shrink in the middle of the, you know, a thick area, especially where a thick meets a thin. So it is possible to make a better casting, but it's very difficult to make a perfect casting. Basically, you have to put so much metal into the heads that are going to feed inside that casting so as it's cooling, it's bringing in liquid metal and bringing in liquid metal. It's very, very challenging. I think that in some cases we get asked to make a perfect casting, something that's so smooth on the outside, something that doesn't have any surface finish issues. And we really encourage our customers to say, hey, look, this surface finish, while it might look a little rough, if it's not going to impact your part at all, or it's not going to carry oil out of your furnace, we'd prefer to leave that chromium oxide on the outside as a benefit. So again, it's difficult to make a perfect casting because there's so much shrink factor in this metal, but you can separate a good one from a bad one if you're paying close attention.
It is. So now let's talk about the chemical composition and laboratory testings, procedures, and quality checklists, because we talk about HT, HU, NC11 or HX. First of all, can you explain us all the HX or superalloy? What's NC11? Some people call it superalloy. Some people call it HX. What's that thing? How I see it personally is a higher level of alloy, which will resist more temperature and carbon, and it's more pricey. That's how I see it. But you know,
yep. I think that's a good way to put it. What it should do is exhibit a longer life inside your furnace. Right. So when we say superalloy, we mean something that's typically had cobalt or tungsten or columbiums, some of the specialty additives that have been added to it. HX is just a very high nickel content alloy, like NC11. NC11 has, you know, higher nickel, higher chrome, but NC11C has that higher nickel and chrome, but it also has cobalt added to it. So
and what will be the difference between one and another with cobalt and one without cobalt?
Right. So the cobalt is going to be able to go up to higher temperatures, okay, and is not going to be something you're going to want to put through a furnace that has any kind of fluid quench in it either. Right. So if you have a high temp situation, and if you have an extremely expensive furnace to bring down, which I'm sure most people think theirs are, but in certain circumstances where you're like, look, this thing cannot come down, we're going to go ahead and invest in these piers being made out of, or these tubes having cobalt in them or tungsten in them. Really, really expensive furnaces to bring down. They'll invest in that. So they'll get, instead of getting 2 years of life, they'll expect to get 4.
So tell us one thing. What's like when you talk to a customer, and is there like the misconception like just go higher in nickel, and chrome, and you'll get more life out of it? Do you fight that battle a lot? Besides telling them, well, we could add some cobalt or a little more niobium, and you can have a better application, and the customer keeps pushing for higher nickel and chrome.
Yeah, we certainly get that when it comes to salt pots, and people think that, well, you need to have extremely high nickel content, but oftentimes people just use 309 in a salt pot. So again, if you can accurately describe what you're trying to get out of the thing, out of the unit that you're putting in there, and whether or not it's being quenched and how it's being quenched, your furnace alloy supplier ought to be able to tell you what's most suitable. But there's a ton of options, and so I would lean in heavily on them to say, well, I've always bought this out of HT. We've always gotten 18 months out of it. We're really trying to extend this to 2 years. The option might be to add a little more nickel or a little more chrome or some cobalt. The option might be to thicken up that area on your casting. We have a constant battle where we fight people wanting to have a thinner wall casting to get more part loading inside your furnace. But sometimes you're really sacrificing the life of that casting. Now I'm talking mostly about fixturing and trays, but you sacrifice a lot of the life of that casting, or to say, okay, I'm going to be able to get 6 more parts in here. But people can do a cost benefit analysis on that and see what they think is best.
I believe that's a great observation, the one you just made, because also as commercial heat treaters, and I just had a great podcast with John Hubbard, former president former CEO of Bodycoat. He basically told us, you want to be heating parts, not castings, right? And that's the conception from the other side. You want to optimize as much parts as you want to have inside the furnace, and not heat treating castings. And I have seen amazing castings, very big, very robust, very solid, and you go like, whoa, that's like a ton of casting there. Like, and then might be heat treating 300 kilograms of parts, but that's what it takes for the arrangement. Well, so
there's unfortunately the size of the casting and the weight of the casting. Sometimes you can thin down some of that weight too with using the higher grade alloys, right? But oftentimes what we see is people going to a lower grade alloy and just being okay with it only lasting, that tray is only going to last for X number of months, instead of a higher grade or a thicker wall would last for 2 years. They just can't take the part loading ratio.
Well, it becomes a financial part of the business, right? You don't have always the accuracy that you're going to have cash flow for the next 2 years, right? So you expect to aim for the next 6 months, right? Because castings, fixturing and spurts are a big part of the cost structure of a heat treat shop.
Absolutely,
they're pretty big. It's maintenance. Well, it's capital investment, but that's initial capital. Then we go payroll. We got energetics, gas, electricity, furnace maintenance, oil quench, and of course trays and fixtures and spare parts. So that's like the big part of the cost structure of a heat treat shop. So it's a very important decision.
Thankfully, in a lot of all these alloys that we're talking about, they do have a value at the end of their life. So I want to make sure all your viewers, nobody's throwing those things out into the regular yard with their other mild steel scrap. Make sure that you're getting the value of those castings and fixtures at the end of life. We should recommend that you're getting, 20% of the value of the original price, depending on the, how complex it is for your castings, depending on the nickel pricing as well. But make sure you're getting value out of those things at the end of the life.
And that's a great comment for the follow-up question, that it's chemical composition.
Yeah.
So we talk about HT, HU, HX, or NC11, 330. So how do you? Well, it's based on the nickel chrome or the other elements that it's on the casting. But what's the procedure to check that a casting is on the level of tolerance? Or the level of allowance of each thing, right? Because there's a lot of companies, and I'm not being specific, that nickel is like the big player here for the money, that they go on the lower limit of nickel liquid percentage in order to give you the alloy grade, right?
Sure.
And it's getting more and more common whenever you actually receive a part or you sell a part, that they want to have the chemical composition report.
Yes. Yeah, and that's a great recommendation that I would have for your viewers too, is request the spectroanalysis from your alloy supplier. I think it's an important thing for people to do. Every single person ought to be able to provide that to you. If they're a reputable foundry, that shouldn't be an issue. But typically in our industry, we see people using spectrometer analysis, where they're making a small burn into the metal, and there's a analysis that's done of the smoke that comes off of there that determines what it is, what chemical composition is in there. We also have handheld operations that you can do that with. It's critical when you're using a handheld that you make sure you clean up that metal surface. You don't have any carbon on there. You don't have any contaminants on there. We think the Spectro is more accurate. We use our handhelds for basically getting it close, when we're out in a scrapyard or something like that, or we're looking at two castings that look identical and we're trying to see which one's HT and which one's HK. A handheld is very useful for that.
Are the handhelds affordable, or they're like super expensive? I mean, for like a captive.
They're very expensive. Yeah, they're very expensive. They're $25,000 to $35,000, right. Which you don't want to have somebody dropping one of those out in the yard, and they do need to be calibrated properly. The other thing about some of these handhelds is that they don't have the range. They might be really good at looking for 304, but if you're trying to pick up cobalt, or you're trying to pick up higher nickel alloys, they don't necessarily have those curves inside them. So ask for a spectroanalysis. Most of those spectros aren't picking up what the carbon level is. People have to do a separate analysis for the carbon, but in the casting process, you ought to be able to control that carbon also. So we think Spectro is the best way to go. There are things that I would ask an alloy supplier about how they maintain their Spectro. What outside people do they have come in and verify, hey, if you're telling me that this range is 34% nickel to 35% nickel, how can you verify that? What's your independent verification? See if they have A2LA accreditation, which is like a lab accreditation that some foundries have. So those are the two primary ones, though, the spectro analysis and then the handhelds.
And I assuming to do a spectral analysis of a pore is like standard procedure, so it shouldn't come with a price, right?
No, it shouldn't. If analysis, they ought to have it on their own if they've got any kind of quality system. But what we do is we'll take a dip out of when the batch is ready, we'll take a dip out, make a little coupon. That coupon gets sent across the foundry over to the Spectro, polish it, test it. If there's any additions that need made, we'll make those additions. You got to let it sit for a second and boil in, and then test it again and get final approval. So you ought to be able to see those final approval spectro analysis for anything that you get.
The reason I'm asking that is that there are suppliers in the business, like, let's say thermocouples, that you also, there's also chemical composition of thermocouple, right? And you want to have the thermocouple certificate. And there are companies that actually will sell you thermocouple, but they will charge you an extra just for the paperwork. I mean, for the certificate, right? And, yeah. I find that really annoying, because it's you're buying a product from them and you're asking to have the certification that actually what you're buying has in it what you're paying for, and they want to charge you to email you a PDF, right? So
yeah, that's strange.
That's strange, but that's a great. That's a great observation and a great. Advice.
Yeah, that's on how to identify the metal characteristics. Obviously, the quality of the casting you're getting is going to start with the design of that casting. Mm-hmm. And so if somebody's designing you a new casting, they ought to be putting that design through some type of simulation software to see, as that metal cools, where are going to be the likely errors in the casting. People use MagmaSoft as a common software to look at, to analyze where likely issues are going to be. If you're making if you're buying a radiant tube, some of our customers will ask for some type of a leak test to be done of the tube welds, typically just like a soap test or something like that. Some will ask for dipenetrate. Sometimes we get asked for X-rays. We have an X-ray, but depends on geometry whether or not you can actually get a good X-ray in some of these castings. But destructive testing is always something that when we do a first run especially our fixturing customers. They always want to see a destructive test to make sure that everything's solid. So those are some good examples of things people should be looking for.
Okay, now you mentioned something that we also want to talk about, radiant tubes, right?
Yeah.
So you don't cast a radiant tube the way with lost wax or green sand or set, do you?
No, the tube itself is made out of a very unique process called centrifugal casting, which is absolutely fascinating.
That's why I didn't want to touch base on the subject first, because we, how I call it, static castings, right?
Hmm.
That can be done on green sand, air set, or lost wax.
Hmm.
That's like this type of castings. But whenever we talk about centrifugal castings, and I have seen in your company and in other foundries, it's pretty brutal. It's pretty amazing process.
Yeah,
Can you?
it is cool.
It doesn't get it doesn't get old. I mean, you can just watch it and watch it and watch it, and
Yeah.
and it's like hypnotizing. You see that thing spinning
Yeah.
and
So
you see the red.
the process is basically you have a tube mold that's of a given length. Let's say, for example, 120 inches, and that tube mold is 6 5/8 outside diameter by 120 inches long, and the tube mold is sitting on a machine spinning and spinning. The inside of that mold gets coated with a ceramic spray, a nice thin layer of ceramic spray to keep the metal you're going to pour in there from sticking to the inside of the mold. So the inside of the mold is the same OD as the tube that you're wanting to get, maybe just slightly larger. So you'll put end caps on this spinning tube that's been sprayed with ceramic. You'll heat your metal up to 3,000 degrees, give or take, depending on what you're pouring, so it's nice and viscous. And then you'll measure out exactly how many pounds you need to make a 6 5/8 inch tube, 120 inches long, a 1/4 inch wall. So you get your math going and you say, okay, that needs to be 125 pounds, and you'll pour that exact amount into your furnace, into your mold that's spinning very, very fast, and the metal centrifugally, the centrifugal force of the metal pulls it to the inside of the mold wall, and all the impurities and things like that will go to the inside of the tube, which is nice. It's a very, very solid tube typically. You'll spray the outside of the mold with some water so it cools off that tube. The tube shrinks just slightly, and if you've done everything right, won't stick to your inside of your tube mold wall. So you can put an extraction device in there and extract that tube. So now you've got a seamless tube that is got great metallurgy, great grain structure, and perfect for a furnace roll or a radiant tube.
And there's a bunch of steam over there. I seen the process,
Yes.
and there's a bunch of steam, and there's a guy fighting with the tube. So and if you go on YouTube, because I did it before this podcast, there's a bunch of non very not very low safety operations. I mean, there's a bunch of companies that does it on a very primitive way. Also with the 4G process, it has the risk to actually
Definitely.
to pour metal. You're gonna deal with risk. It's hot metal, right?
Yep.
So you have to take precautions.
But when it's spinning around at 3,000 RPMs in a tube mold, and it's 3,000 degree metal spinning into a 3,000 RPM tube. It's exciting. It's exciting, and it needs to be done properly. It's one of those processes that you want to make sure people are standing clear. So it is awesome to watch, though. So we'll take those, and then we'll test them to make sure that there's no cracks. We'll cut them off and get to the right length. Blast the outside of them. Some people want the inside of them blasted, and then we'll affix those to a U-shaped piece if it's a radiant tube that's a U tube, and the U tube, the U portion, will be cast typically in air set, and we'll get that weld to be beveled up and dialed in. So centrifugally casting tubes has its limitations, right? There's like, for example, some casting machines can only go to about 150 inches long. So if you have something that's 250 inches, then it's going to need to be two pieces, so it'll have a seam in it. So there are some limitations. Obviously, every single OD that you want requires a different mold. So the OD is what controls the mold size.
And also for centrifugal casting, another application will be furnace rolls. as well? Well, you will stick to stainless steel parts on each side, and you'll machine them so you'll get a roll. So also centrifugal is not only for radiant tube but as well for rolls. Is there another application I'm missing for centrifugal castings besides radiant tubes and rolls?
We do some things where people actually use centrifugal casting as a spacer, where
Okay.
you'll cast it 8 feet long, and they need little spacers that are 2 inches long. It's a pretty inexpensive way to make spacers. Some people use them in baskets instead of stack posts because they want them to be removable. So they'll put a centrifugal casting inside there for that. We've made mud pumps for the mud pump industry. People will centrifugally cast something and then machine the OD and machine the ID to make an actual pump body. We've made for the galvanizing industry, we make different kinds of bearings that go into the galvanizing process that are made out of a stellite material. So yeah, there's some different materials, but primarily ours are used for, like you said, radiant tubes and furnace rolls.
And also there's a petrochemical application, right? What would that be for?
So certainly in the petrochemical, there's all kinds of applications. Worko focuses in the petrochemical, the aerospace and the heat treating space. For the petrochemical gas cracking furnaces, we're making some things for different kinds of petrochemical processes that are primarily I don't know. So I mean, that's probably not something we want to keep in the.
I'll get you back, no worries. So talking about, we have talked about casting as a whole, right? The casting process, the chemical composition, static castings, centrifugal castings, high resistance alloy. But on this industry, what are the most common mistakes or misconceptions on castings? When you're talking to customers, when you're talking to heat treaters, that to buyers, because castings are something that has their level of investment, right? What are the most common misconceptions on castings?
So I think the two that are the ones that we've talked a lot about in this podcast, but choosing the wrong alloy for what you're doing.
Choosing the wrong alloy, number one.
Yep.
You see it all the time.
We see it all the time. Yeah, people are like,
is there ways that you're on the phone just nodding your head and go like, oh,
they're convinced. They're 100% convinced like, this is the right thing. You're like,
they're spending money, and this is not one of the like. All right, you want to spend money, so be it, right? But
yeah, they're like, well, it says here on this print, and so that is one that people waste a lot of money on, and in some cases under alloy themselves and don't get the service life that they were expecting, and they come back and they're unhappy. So that
on their alloy will maybe just on a regular slang, if they go cheap, they will under alloy themselves. Is that what you're saying?
Yes. Yeah. Sometimes they'll say, look, we're going to put this HK casting in here, and here are our expectations, and we're saying, look, you're running at 1850. We don't believe that that's a good application for you. You can put it in there, but after 8 months, it's going to start to warp, and you're not going to have the life that you want. We'd highly recommend this, and some people will listen, some people won't. But again, when I need plumbing done, I call a plumber. So when you need alloy, you should probably call somebody that knows about alloy. I think another one is the thin material sections. John Hubbard and a lot of different commercial heat treaters that I've talked to over the years, they're always wanting to make it thinner and make it, so that you're heat treating parts. That's what you get paid for. You don't get paid for heat treating castings. Unfortunately, it's a necessary concept that there's a certain level of casting that has to be engineered, and we have guys, and most of your suppliers would have guys or gals that would say, hey, you need it to be this big to hold up to this temperature in this environment with this quenching medium. And so if you're questioning that, you should be able to put them on the spot and say, hey, can you engineer me something that's going to hold up into these conditions? So those are the two main things I'd say would be too thin a wall, too small of a casting, or choosing the wrong alloy.
Are there guys who want to go too thick?
Not typically. We do see some when it comes to some of the furnace roll concepts, where they just want to keep getting thicker and thicker and thicker, and assuming that that's necessary. But in some cases, you get
And they also assume that the price is going to stay the same, right?
correct.
Yeah.
But eventually, you get to where the weight of the actual tube or roll in that case is a problem. So I would trust your alloy supplier. If they're doing their job, they should be able to give you advice in that arena.
Right. Another common mistake that you see around.
I think those are the two primary ones.
I'll tell you one I see.
Yeah, what do you see?
I see. Well, this is on the tray side. Some heat treat shops, they actually place their tray on the floor, right, and they stack the baskets, and they start loading the load, right, and they'll pick up the fixture with the forklift, bah, just hitting the tray, right. So that will actually harm a lot the life of the tray. So just besides, instead of doing that, we actually have like a small steel structure that we actually place the load over there with a forklift or with a dolly car, and with some rollers, and we're not hitting that constantly, because I've seen that over and over and over in many heat treat shops, that they just place they just place the tray flat on the floor. They assemble the load, and they'll just come with a forklift, and they will just hit the end of the tray, and that will actually hurt a lot.
I think that material handling, that's a great mistake that we see all the time. That this basket, typically like with a lot of rod frame baskets and tray setups, like you're saying, where somebody just comes in and grabs them. If you can just do anything to avoid that impact, these things are not made to withstand that level of impact. So,
especially when they're hot, and I've seen applications where they use trays on car bottoms for normalizing or annealing processes, and the load comes out, and there are trays over there loaded with, let's say, billets of steel or something, and the tray is red hot, right? And the guys, they just pick it up with the forklift, and they just hit the tray, and at temperature that will harm a lot the structure of the tray. I see that a lot.
Yeah, I think the material handling is worth the investment on the front end when you're saying, how are we going to pick this thing up? How are we going to dump it? That is huge. It's obviously you've got your employee health issues of how you're going to do the loading. That are, we see a lot of people that are, they're loading baskets while they're sitting on a tray instead of getting them up. But how you're going to get those off and into your furnace, or back from your furnace over to your loading station, that's a great mistake. I think that's good advice.
Yeah, because material handling is something that we need to, it's a challenge for all the heat treat shops, because we are dealing with heavy stuff. So when you talk about material handling to some of the companies, they think they're going to be plastics or ceramics or electrical components that will be on conveyors, but we're dealing with a lot of stuff, right? And one of the I believe I mentioned this in a previous podcast, but the thing with automating the material handling is also very affected by the distortion. We're going to have some distortion as the part of the tray or the basket begins to quench or to heat treat repeatedly. So there's going to be kind of an offset. So that's like a challenge in order to automate robots loading and unloading stuff. I don't know if they ask you these questions. Is there a way to use robots on the handling?
Certainly. I mean, when you're doing something like that, though, you're going to want to have a casting process that is providing a very repeatable part. So we have customers that want us to actually weld tags on and things like that, so they can know that this is number 3, number 40, number 62. But eventually, that casting is going to start to warp, and when that happens, it's either going to not fit in your process or it will. You can straighten fabrications. We have a lot of our customers that buy their fabrications because that 330 is more ductile and can be straightened. But straightening a casting, once it starts to warp, you're typically going to break the thing.
So
But another common conversation.
Go ahead, Chad, please.
Yeah, another common mistake that I see in that arena is flipping over your trays. You know, one tray that may be reversible, because as it starts to get a little bit of a warp, flip it over, it'll take the shape of whatever it's sitting on. Same thing with your baskets. You know, if you have a stack of baskets or a stack of fixtures, try and not always have the same one on the bottom. Keep track of rotating the top one to the bottom, and the bottom one to the next one up. Do that all the time. Make sure your operators are doing that, and you're going to get a lot more alloy life.
Fantastic. So now you mentioned something that it's pretty handy on the follow-up question. Castings versus fabrications versus ceramics, right?
Mm-hmm.
You mentioned that some application is better for the other one. What can you tell us about when to use fabrications instead of castings? And another question that we get a lot, ceramics, the ceramic applications on heat treating. So
Sure.
two questions.
Okay.
Where to use fabrications instead of castings, and what about ceramics? Do they work on this industry?
Sure. So I'll address the ceramics one first. So typically when we see requests for ceramics, it's going to be in how your furnace is heated with a radiant tube heater. People are thinking ceramics are a good idea, and that they're sold as lasting for a long time. What we found is the heat treating process is pretty rough, and the ceramics are very fragile, and going in and out of the furnaces is not always a pretty process. So we find them to be a little dangerous to be taken in and out. And if you bust one of them, there's no fixing it. Also with the ceramics, their geometry is not quite as, you can make anything, a casting basically in any shape, whereas ceramics are, typically not as, they don't have as many shapes available. There's a lot of lead time issues right now with ceramics as well. A lot of those coming from different countries that are just having a lot of lead time issues. So when we steer people away from ceramics, they haven't really perfected how they make the return bend fit onto the tube. That's another area of concern that I have with ceramics versus a casting. Keeping in mind too, the casting will have an inherent value at the end of its life, whereas a ceramic will not. So, like I mentioned before, the castings always will have value to you after they've even ended their life in their furnace. So to the second question, the fabrication versus castings, we find a lot of our commercial heat treaters like to use fabricated baskets or fabricated fixtures because they want to have the flexibility. Today they're getting in, a couple of giant rings they want to put in a basket, and tomorrow they're dump loading in nuts and bolts, and the next day they're doing some car part. I think that the fabrication versus the casting, if you have dedicated product that you're running over and over again, that is a good opportunity to look at a cast fixturing. A lot of times the proof of concept thing that you're saying, I want to prove this heat treating process out. Can you whip me up a fabrication or 5, and we'll do the proof of concept with the fabrication, and if this works, then we'll move on to the casting, because once you move to the casting process, you're going to have an engineered design, then you're going to have to make a pattern out of it. The pattern's going to be made out of plastic, and it's a heavily engineered product. It's typically expensive. It's very rigid. Once it is like that, this is the product you're going to get. Whereas a fabrication, you can make little tweaks and adjustments. So commercial heat treaters needing flexibility, we typically recommend going to the basket route. You can make different grids and different fixtures to hold parts if you have parts that you don't want to touch each other. If you're doing some kind of sensitive shaft that can't be loaded in and touching each other, you can make different kinds of grids to hold those things apart. And then if you get that job and you're going to need to do a bunch of them, then you can go into the casting route for that. So that's kind of the fabrication versus casting process, in my opinion.
Thank you for sharing that with us, Chad. I think that's very valuable. As a commercial heat treater, you want to have flexibility. So the basket is the way to go. But sometimes I'll tell you a challenge of us commercial heat treaters. We want to outsource parts from a captive, and the captive, they run on trays and fixtures which are cast, right?
Mm-hmm.
And they want to go, well, I want to outsource part of that material because of a spike or something, and you want to spend all the money on the on the castings. I mean, because you have baskets, and it always struggle with the customer, the negotiation of who's going to pay for castings. Because I'm the one who treats your parts, but you're the one that supply me the cats. So that's a constant.
But it is a
challenge for
from our standpoint. When we went into that, we can provide, and most of the people who have fabricating and casting capabilities can provide some of an option to rack those or structure those things to go inside your existing basket. So we do that a lot too.
So you have a way to supply structure to the baskets that can be on a like a hybrid, not to buy the casting itself. I didn't know that. That's great to know.
Yeah. Typically, people use pressure welded grids to do that. We've made multi-layer racks that will go inside somebody's basket. Because usually that's when somebody's doing some type of a shaft or something that can't touch the other shaft, and it needs to be standing up to get the quench medium around it. So we'll buy multi-level racking fixture out of a fabrication. It's a pretty inexpensive way to go, especially if just like, oh, I don't want to buy a dedicated tooling for this, but we're going to get some of these. I would look for some type of a fabricated racking fixture is a great way to go in that situation.
Great advice. One last question, and maybe you get this one a lot. Why does nickel pricing fluctuate that much?
Yeah, we do get that question a lot.
Right.
So back when nickel for years was in the $3 to $4 range, and then in 2007 there was actually a short supply of nickel. So nickel is mostly kept in the London Metal Exchange, and if you go online and Google LME nickel, you can find out the pricing for that. The pricing you see there is if you're going to take a truck and go buy master sheets in London. So what we buy is actual bags of it. So they add an adder to the pricing on the London Metal Exchange. So the London Metal Exchange, everything is traded in dollars. And so you've got two components. You've got the supply and demand, the actual availability of nickel, and then you've got the value of the dollar, how many nickel units can a dollar buy. So what we believe we've seen in the last 5 months since the middle of the summer last year is that the United States is printing a lot of dollars. The dollars are more available, so the dollar is weaker, and so it doesn't buy as many nickel units. So if you're looking forward and you're saying to yourself, I wonder if the dollar is going to continue to weaken, and if it is, there's typically an inverse relationship, and the nickel price is going to continue to go up. One of the things that people talk about all the time from a demand side is the nickel going into batteries. And that's been a big conversation. Is there going to be a nickel shortage because they're using it in batteries?
Oh,
we've been hearing that
for EVs.
Yes. Yep. Yeah. So that's a component inside the battery is raw nickel, and so we haven't seen a run on that where that's actually impacting the supply side, but it's something to be concerned about in the future. When nickel gets to a certain level, the Chinese can start using a nickel pig iron that can offset some of the demand for actual electrolytic nickel, which is what we buy. It's just a pure form of nickel. So we've seen two things: supply and demand, right? So that's going to be the London Metal Exchange's supply that they have, how many days they have in their warehouse. It's something you can see, and you can compare that year on year. What we're seeing to be more impactful in the last several years is monetary policy and the value of the dollar. I don't know if that helps or not, but
I believe it's a great explanation, and I didn't know nickel was a part of batteries, so it will be interesting to see what's next, right? And if there's a shortage, and figure out how to take care of that shortage. So let's go with the heat treat hack of the day.
So I think that it's going to be that everything you put in your furnace is going to take the shape of whatever it's sitting on. So let's be very cautious as in your future picture. If you're putting fixture on the shape of your warp tray, same with your hearth plate, same with, whatever your tray is sitting on, it's going to your furnace and work your way up. I would say another one is when you're having your burners tuned, make sure they're tuned by somebody that knows what they're doing. We've seen a lot of radiant tubes in the past that, have a hole burned in the wall, and the customer's upset, and we're asking, well, obviously your burner was pointed at that tube wall, and nothing's going to be able to keep up with that. I think the third thing is greasing of your bearings, especially in your furnace bung assemblies, your fan assemblies. Those are, if you have furnace rolls, in the furnace roll bearing assembly, those things are operating at very high temperatures, and that grease, if it's not kept up, will burn out and will ruin your shaft, whether it's on your furnace roll or your fan. So those are three good ones I think to keep in mind.
Can you repeat the first heat treat hack, because I lost you for a second, Chad?
Sure. So let's keep in mind from a heat treat hack standpoint, anything you put in your furnace is going to take the shape that it's sitting on. So if it's sitting on a bent tray and you've got new baskets or new fixtures, they're going to take the shape of that tray. If you're putting something on a busted up looking hearth plate, it's going to take the shape of that hearth plate. So just keep in mind, everything you put in your furnace is going to take the shape of whatever it's sitting on. So look at your bottom up and build your furnaces from the bottom up, so you be sure to get the best life out of your very expensive castings.
So there you go. That's a heat treat hack from Chad Wright. And I believe that's great added value for the audience, because those are things that because you deal with castings, every day from 9 to 5. Well, I believe from 9 to 9. And just to conclude the show, Chad, this is the last part of the show, the one that actually I enjoyed the most. One personal advice or experience that you would like to share with the new generation of heat treaters that you have learned during your career? What will you tell that new young engineer? What will you share with that new heat treater that just got hired on a captive shop, captive or commercial shop?
I think for me, it's from a life standpoint, acting with humility, realizing when you're wrong about something, and asking a lot of questions. So I notice when I'm talking to people, young or old, that aren't great listeners, they sit there and interrupt. And I feel like if you're moving into a new business, you're getting into a new career, ask questions and be willing to sit there and listen. You don't have to sit there and have all the answers. So come in with humility, be willing to ask a question for somebody. So many people are so poor at conversations these days because they don't ask each other questions and express genuine interest about the other person. They're just sitting there talking about themselves. And there's nothing I get more annoyed about than sitting there and be like, well, it was great to see you. I haven't seen you in 2 years, and you just talked for 20 minutes about yourself and didn't ask me a single question about me. So I think be conscientious about that, be humble in everything that you do, and don't be afraid to ask questions about the person that you're speaking with.
That's great advice from a very successful professional from this industry. So please take note of that and follow it, because Chad is a very successful president and power player of the industry. So this guy actually has built the company to what it is right now, and he's sure one of the most successful on shows or meetings when these COVID things gets over. And it's always great talking to you, and you're very kind, always sharing your experiences, your knowledge. And I thank you very much for this podcast. Guys, don't forget to subscribe to the channel. We're on LinkedIn, uploading weekly shows with heater players, power players. You get the information for like the main guys, right? So this is what it's all about. We're on YouTube, LinkedIn, Spotify. Please subscribe, hit like, and I don't know, Chad, if you want to say something to the audience before.
Sure. Yes.
Leaving?
I tell you what, Carlos, it was great. It's great to see you, since we haven't seen each other in a while with the whole COVID thing. So it's nice to see you, even if it's just on Zoom. But I appreciate what you're doing and getting new ways to communicate with the new upcoming folks coming into the heat treating space is it's imperative, because this industry is going to be here indefinitely, and so we need people coming into it that are interested. And I'm so excited that you're doing this. So nicely done.
Yeah, let's I hope this is not the last time that we speak. There's a bunch of stuff regarding alloys and castings that we can cover, but it's been a right talking to you, Chad, and thanks for sharing that. So
Absolutely.
I'll see you guys next week. Thanks for stopping by.